Okay, so we're very happy to have Ken McAloon here to give an encore of his presentation from Cornell last month, entitled E Pluribus Unum. Go ahead, Ken.
Okay, so the title is A Pluribus Unum to catch the idea that the Models of Peano Arithmetic is not like set theory, which, you know, it was issued from the head of Cantor, fully grown, or Galois theory, things that have this moment of authorship, this origin myth. This subject is actually sort of a confluence or collision of things that happened over time, and really it sort of starts to take off as a subject in itself only in the 1970s and 1980s. And lots of ingredients go into this, like model theory, proof theory, etc. And speakers came, and McAloon Rignac, and it was a bit of a joke from the Cornell session, where there were so many Poles around that I hyphenated my name, because Rignac would have been my name had my paternal grandmother been my paternal grandfather. And that name is from the southeast of Poland. So, page down, why doesn't it go down? Page down. Okay. Oh, the page isn't moving. Oh, there it goes. Okay, got it. Okay, now the prehistory of the subject goes back to Dedekind and Peano, and these mathematicians were thinking in second order terms. They were trying to characterize n as in a categorical way as the standard integers. But then the development of first order logic by Frege, and then the introduction of first order theories, which were designed to capture mathematical practice. They had Principia Mathematica, Zermelo, Zermelo-Fraenkel. These are all first order theories. And then in response to that, you had Hilbert's program to establish the consistency of mathematics formally, and this gave birth to the subject of proof theory. And already in 1929, arithmetic gets into the act, where you have Pressburger arithmetic and quantifier elimination. And these guys were tough back then. Tarski assigned it to Pressburger as a master's thesis project. Quite remarkable. Now, of course, the big event in the 1930s is the Gödel theorems. You have the completeness theorem, which in and of itself would easily yield existence of non-standard models of Peano arithmetic, but it's not clear, at least from what I can see, that first order Peano arithmetic was even formalized at this point yet. I mean, and Gödel himself, in his incompleteness theorems, does not deal with Peano arithmetic. Instead, he deals with the arithmetic, he deals with Principia Mathematica and related systems. Now, his work, of course, was in response to Hilbert's program, and already von Neumann and others had proved consistency of fragments of formalized arithmetic or formalized set theory. But Gödel doesn't talk about Peano arithmetic as such. And the advantage of this is that he can assume certain facts about number theory without having to prove them in Peano arithmetic. For example, the Chinese remainder theorem. As I have a question mark there, because as I remember Gödel's paper, he does not prove the Chinese remainder theorem. He just assumes it's true. But this whole question about the origins of arithmetization, the origins of the second incompleteness theorem, this is a historian's delight. I mean, the incompleteness theorems were announced, at least the first incompleteness theorem was announced at a conference in 3031 in that era at Königsberg in Prussia, in Germany. And von Neumann was there, and Herr Braun was there also, and Gensen apparently was there. So it's amazing congeries of logicians. Now, of course, Gödel's theorems introduced self-reference and diagonalization. And there's a whole interesting historical topic. What was the formulation, the original formulation of the first incompleteness theorem? Kripke and others have alluded to this. I know in seminars and other places, you have books going back early. We know that the arithmetization, as we know it, where everything is done in terms of numbers, was suggested by von Neumann. As von Neumann apparently said to Gödel, the whole thing would be a lot easier, a lot more palatable if it was all about numbers. Now, Geifman made some remarks at Cornell saying that the original formulation was in terms of finite sequences. There was some language dealing with finite sequences that he used. And then when he went to arithmetic, he got the sequences using the Chinese remainder theorem. But the subject of, what's going on at the very ground level in this and these incompleteness theorems is subject very much alive and well. We had Saeed Saleh's MOPA talk a week or two ago. We have this paper by Smerinsky called The Early History of Formal Diagonalization. I used to think that I knew this stuff, I've worked on it, and published papers and all that sort of thing. But the more I read up on it, the more I realize how little I know. I mean, it's still very much alive. And of course, that includes Ross's theorems, which people continue to work on. Now, the plot thickens in the 30s because you have Tarski in the undefinability of truth. You have Tarski's paper on the concept of truth in formalized languages, the birth of model theory. You have Skollem's construction of non-standard models. Here, as far as I can tell, is the first formulation of first-order piano arithmetic. And his is very elegant construction, so it looks like an ultra-power construction. It's the non-standard model is a model of true arithmetic in this case. Now, recursion theory, the golden age of recursion, 1930s. You have the various models for computability, Herborn-Gödel, recursive functions, the lambda calculus, Kleini's T predicate, and of course, Turing machines. You have Church's thesis. Now it's called the Church-Turing thesis, which I say is fair enough because although Church actually wrote the thesis, expressed the thesis in a published paper before Turing was involved, but it's fair enough because Gödel apparently only began to believe Church's thesis after he saw Turing's work. Then Turing actually was at Princeton. He presented his paper and stayed on to do a PhD thesis with the title Systems of Logic Based on Ordinals, where he iterated the consistency formula. So he took piano arithmetic plus consistency of piano arithmetic, then piano arithmetic plus consistency plus the consistency of those two, and you iterate this consistency statement, and you iterate it out far enough, and I think you capture all of pi 0, 1 truth. Now, at a conference back when, maybe the late 60s, early 70s, we had some kind of stroll. It was in the summer, and I had the chance to talk with Kleini, and I asked him what was motivating, what was their motivation back there in the 30s. And he simply said, well, the Germans had this truth theory, and we were trying to catch up. Now, truth theory, is Hilbert is sort of credited with launching it. And there was a Hilbert Bernays book, which, according to what I've been reading, was really completely written by Bernays, but Hilbert wrote the introduction. But Hilbert was always given first authorship on his books. There was also Hilbert Cohn-Vossen. There were couple of books where Hilbert was the first author, although he wasn't alphabetically the first author. And this book has the Hilbert derivability conditions and the proof is sort of now standard proof of the second incompleteness theorem. That's in volume 2. Also in the 30s, you have, and into the 40s, you have Gensen's work, which is brilliant, original, faithful to Hilbert's program. He himself, as I said, he was at that Königsberg meeting, but he was a graduate student at Göttingen. He worked with Bernays. He also worked some with Hilbert and Weil. Now, running back to my day, 60s, 70s, 80s, certainly the 60s, I think we didn't understand. Very few people understood Gensen and what he was up to. And we thought the consistency proof for piano arithmetic, given Gödel's theorems, was kind of quixotic. But on the other hand, epsilon zero, that was cool, a little vague, but cool. Another thing that made it a little tough was that although we had to read mathematical German to get our PhDs back then, his work and Schutter's were all in sort of classical German. They were not all that accessible. But there were Anglo-Saxons working on proof theory, like Tate, Spector, Curry, Howard, and all, and people elsewhere, other. So the subject was moving ahead, and now the Curry-Howard isomorphism, of course, has become very, very important in automatic proof verification and also lambda calculus everywhere. Then they have the après-guerre, and first you have the work of Leon Henkin, his elegant proof of the completeness theorem, Henkin's problem, the formula that says I am provable, Loeb's theorem, which probably was developed in order to solve Henkin's problem. Henkin also formulated the completeness theorem in piano arithmetic, which was turned out to be very, very useful. He also showed that the order type of less than and countable non-standard models always look like this. Then jumping down, and also in 59, you had Tenenbaum's theorem that worked that no non-standard model had recursive operations. And, that was considered very forbidding at the time because it meant you couldn't construct explicitly a non-standard model. And you also had the non-finite axiomatizability of piano arithmetic, which was shown by Riel-Nodzewski already in 1952. And this is a very beautiful proof, as I kind of remember it. It used non-standard models. It was very, very elegant. Then the après-guerre comes to an end, but with a punch. You had a book, which I actually managed to find in the Massachusetts public library system. There was UMass Amherst had a copy of this book from 1960, the book itself, Infinitistic Methods. And there's several, classic papers in there. One is the McDowell-Specker theorem about elementary end extensions. This is, a cornerstone of the subject now. I checked that this was used as recently as 2006 by Jim Schmerl in a paper on minimal end extensions. You had Montague and Mostowski both doing work on non-finite axiomatizability of PA and other theories. Montague's paper was very useful too because it did a lot of sort of the busy work of how you got piano arithmetic to do things for you, how you sort of do set theory and other things, kind of computational things inside piano arithmetic. It was a very useful paper. And then Dana Scott had a short paper, but as always with Scott, some very interesting things kicking around, where he said that while there were plenty of non-standard, so to speak, models of geometry, non-Euclidean geometries of one kind or another, it was very difficult to do that for piano arithmetic. And So this makes it difficult to show things are independent by building non-standard models. Of course, this is exactly the sort of dam that was breached by the Kirby-Paris work in the late 70s. And then you also had another important paper by Pfefferman on the arithmetization of metamathematics in a general setting. Again, in Fundamenta in 1960. Another subject area that contributes to models of arithmetic was hierarchies of recursive functions. Now, reportedly, Gödel said that a hierarchy of recursive functions was an important open problem. I think it's still open. Church and his students, for example, Joel Robin, worked on hierarchies of subrecursive families of functions, the 50s, 60s. Now, some gossip. There was someone who wrote his thesis on the church, but switched fields immediately after, telling Ralph Abraham, who was a friend of mine, that the field was boring, but we won't go there. How history, however, has more than validated the work on hierarchies of, subrecursive hierarchies. And this, of course, happens when models of Peano arithmetic really starts to catch up with proof theory. Another important piece of work on hierarchies was the Gregorchik hierarchy in 1950s. Oh, God. I just had to shut off the phone. It was a spam call. Okay. So in the 1960s, also, you have stalking Hilbert's 10th problem. The work by Michael Rabin, non-standard models, the independence deduction axiom, models of arithmetic and Diophantine equations. You had Martin Davis's work, and you had the Davis-Putnam-Robinson work. Well, you're almost there. Just need a Diophantine equations whose solutions exhibit exponential growth. And that was then, that polynomial was discovered in 1970 and yielding Matijasevic's theorem, which is usually referred to as MDRP. I might point out, though, that Julia Robinson was a graduate student of Tarski, actually, at Berkeley. Now, in the 70s, things really start to come together. This is early on in the 70s, throughout the 70s, Chaim Geifman wrote several important papers mostly on types in Peano arithmetic. And for example, you have this paper here called Models and Types of Peano's Arithmetic in the Annals of Math Logic. It's, it's almost 100 pages long. This is this is hardcore model theory, and it has gems in it, such as the minimal end extension theorem. He also wrote this key short paper on the Matijasevich result, where the sigma 0, 1 is the same as existential 1, where you could sort of eliminate the bounded quantifiers. That turned out to be a very handy result. That was used a lot. But also, now more things coming from model theory. The student of Abraham Robinson, Yoram Hirschfeld, wrote a thesis, Existentially Complete and Generic Models for Arithmetic. It was a very beautiful piece of work. Julia Knight, another Tarski student, wrote papers on emitting types in arithmetic and Humph numbers. Alec Wilkie, who was then at the Open University, which is an amazing thing. The Open University ran its courses by correspondence. Those of you might remember the phrase correspondence course. It was sort of the online course of its day. So Alex had, his career had humble beginnings, if you will. And he really has had an amazing body of work and an amazing career. And he wrote several papers, among them giving not one, but two answers to problems, answers to two problems raised by Geifman in his papers. And you had Friedman's isomorphism theorem that non-standard models are isomorphic to initial segments of themselves. And so things are heating up. And they continue to heat up. You had the work of McIntyre and Simmons, thing titled Gödel's diagonalization technique and related properties of theories. Now here I'm quoting Craig Smerinsky. This work was a precursor to the modal logic treatment of provability and diagonalization. And for example, you had the Goswari-Solovey paper in '79, and more recently in this century, Christopher von Bülow has, and I'm sure others have papers on this in this direction. One thing that happened in Paris this time, where I was at Paris 7, Jussieu, which was a campus, example of the bad driving out the good. This campus right on the Seine of the university actually replaced the old wine market, imagine. Jeff Paris was supposed to come to give a talk, but he couldn't show up, something happened. But Harry was there. So we drafted Harry, we pressed him into service, and Harry gives excellent talks. I mean, there's a mixture of, he's very clear and he's very enthusiastic. You could see him, what he was doing was exploiting recursion theory to build models with interesting properties, sort of therefore giving modeling a recursion theory theorem. And recursion theory theorems, I mean, between you and me, are kind of dry, you know. But when you can see it leads to a certain structure, it gives it a kind of life that it didn't have before. Now, another example of work in the area coming from model theory, you have the Abramson-Harrington paper on models without indiscernibles. Now this had really high-powered combinatorics in it using some nasty combinatorial theorems. I contributed a paper in the Transactions on completeness theorems, incompleteness theorems, and models of arithmetic. And one of the things, and this was a proof that the McDowell-Specker theorem requires all of Peano arithmetic. That if you truncated the axioms at any point, at any, say, sigma n induction or something, then the McDowell-Specker theorem would not hold. We also had Ulf Schmerl's extension of Lerb's theorem, which was most useful for working with ordinal notations. I couldn't find a reference to a paper, unfortunately, with Schmerl's that Schmerl published. Sorry about that. You also had the birth in this period of reverse mathematics, Friedman 1975, and subsystems of second order arithmetic. This became a major program involving, you know, Steve Simpson and a lot of other people, and is you know, very, very impressive. The confluence goes on. Now, sort of my dates are a little tricky here. Just rolling back to 71, you had a paper in the JSL by Parikh, Existence and Feasibility in Arithmetic. In this paper, he sort of puts together machinery that sort of says that there are gaps in the natural numbers. You know, there are holes you can't quite reach or get over. You have to leap over them. And Essen and Volpen hyperfinitism is in the background here. But this work was applied later by Jeff Paris to solve a problem with Solovey. And later I'll mention a paper of Patrick Sigelski's, which also uses this Parikh paper. Another also coming this time from the then Soviet Union, you had Mintz's characterization of the provably recursive functions of sigma 0, 1 induction. These being the primitive recursive functions. I got a copy of the paper, it was in Russian, and there I was stumped. But at this point in Paris, we had an Albanian graduate student in the math department, in logic, actually. And his name was Luc Pierre Denis. And he, of course, could read Russian. And so he translated it was a short paper. He translated the paper into French for us. So I have to thank him for that. But the Confluence continues. Complexity theory now gets into the act. Ferrante and Rakov had a nice paper, beautiful paper on lower bounds for how complex a decision procedure for Pressburg arithmetic had to be. And the other people were applying Pressburg arithmetic itself and quantifier elimination and whatnot to automated reasoning. And then also in the 70s, early 70s, you had work of Stan Weiner. I say working in the fields of the Lord because, you know, he was working on hierarchies of recursive functions, and this was sort of subject people weren't paying attention to, although he was quietly developing the Weiner hierarchy. Now, Jean-Yves Girard at Paris, he thought assigning ordinals like epsilon 0 to piano arithmetic was, in his words, stupid. And he developed a system of ordinal notations and a slow hierarchy that took gamma 0. This is much bigger than epsilon 0. This is the Pfeffman-Schutter ordinal. That many steps to outrun the provably recursive functions of piano arithmetic. But his proof is very hard to follow. It used dilators and things. But again, quite impressive. Now, here's a magical period in the development of the subject. I guess I should, the Mancusian period. This is the work of Paris and Kirby and Paris. And here, set theory gets into the act because they were thinking of what we call cuts, initial segments of non-standard models of piano arithmetic as large cardinals in the set theory sense, like weakly compact cardinals, which corresponded to what they then called strong cuts. And they developed this method of the indicators, which showed the great richness of initial models, of initial segments of models. This in some way solved or addressed the problem Dana Scott put forward in the infinitistic methods, in his infinitistic methods paper, that building models, non-standard models, is difficult because of the complexity of the axioms. It's not like geometry. But the indicator method really is a very strong tool for building non-standard models. And their papers were very British. They expressed things in terms of games, where there would be two players, and they would play this game and eventually converge at an initial segment that was a model of piano arithmetic. And in these games, each move was a go. At the nth go, player 2. And but this gave rise to Jeff Paris's first true unprovable combinatorial statement. It's quite nice. A finite set X is zero dense if its cardinality is greater or equal to its min plus 3. It's n plus 1 dense if for every 2 coloring of the 3 element subsets of X, there is an n dense homogeneous subset. And then the theorem, for all n, there exists n dense sets. But his proof of this theorem used the McDowell-Specker theorem, which in turn requires all of PA. The notion of n dense, or especially the notion already of zero dense, captured set theory's notion of infinity. And this finite combinatorial theorem provides an indicator which yields strong cuts where the theorem itself must fail. So this is an unprovable combinatorial statement. It turns out it's equivalent to the one consistency of PA, the consistency of PA plus pi 0, 1 truth. Then, of course, you have Paris-Harrington. This sort of put things on page 1. Basically, it's Ramsey's theorem with the fact that the homogeneous subset has to be one dense, at least the smallest elements of Y. This again is equivalent to the one consistency of Peano arithmetic. And this was quickly published. I think Barwise almost sat them down and insisted that they write it up for his handbook. Onward. Now, this part I know hopefully Laurie Kirby himself will have a chance to talk about this period further in a talk on all of this. But just to say that this was their work then on the Hydra, their proof of showing their work on Goodstein's theorem, epsilon 0. This was a great British moment, and they should at least get the Order of the British Empire for this. Meanwhile, back in Paris, in the late 70s, Paris, Chaim Geifman was a visiting professor. He gave a course on types and arithmetic, etc. We published an astérisque, which is the Société Mathématique de France's journal. And this getting to, have one of these things, publications devoted to models of arithmetic was something of a coup for us in Paris. I mean, this was real recognition by the establishment. And so we got model theory stalwarts, Jean-Pierre Chasser, Max Dickman, and Daniel Lescar into the mix. We also had what the French call action thématique programmée. That means we had some funding for a postdoc and other things, and getting things typed, that sort of thing we used to do back then. And we published a Springer Lecture Notes volume, 870, Model Theory and Arithmetic. And here you see a bunch of new names come in. Peter Claude, Patrick Sajielski, whom I alluded to before, Zoe Chatidakis, Anne Pillay, Pascal Michel, Denis Richard, Peter Axel. Now, Axel actually contributed to this volume basically a thing he had written somewhat earlier, almost the day after Jeff's first combinatorial incompleteness theorem result. And he, in this, it was a very nice paper. And it also raised questions about epsilon 0. And also we got Cherlin and Dickman in the mix, Jeff Paris himself, Wilmers, Wilkie, myself and Chasser had a paper. Then a few other things, we have dropped some more names. We had Kirby Murawski, McAloon paper, and Sofia Adamovich also came to Paris at that time. Oh yeah. Onward. Now, here you have the Ketton and Solovay paper already in 1981. That's pretty fast. Rapidly growing Ramsey functions. Here they used the Wiener hierarchy to do the Paris-Harrington results and other things. They also sort of answer a question that Axel raised about epsilon 0 in the paper I just cited in that Springer Lecture Notes volume. Also, again, to drop my own name and two others, Friedman, McAloon, Simpson paper, a finite combinatorial equivalent to the one consistency of predicative analysis. Now, I'm proud of this because I like to market this as a combinatorial statement Poincaré would not have been able to prove. But unlike Girard, we were shameless and we just claimed gamma 0 as our ordinal for this work. Now, Also had Friedman's work in reverse mathematics led to a version of Kruskal's theorem not provable in ATR 0. Wikipedia says this was done in the early 1980s. And then again, to drop my name and that of Kanamori, we had a version of one of these independence results, which used regressive functions that also come from set theory and had no need for large finite sets. I have a slide with the statement of both the Friedman, McAloon, Simpson, and the Kanamori, McAloon in an extra slide if anybody wants to see the details of these statements. But the key thing here is no need for large finite sets. Now, recursion theory revisited, now, you have papers where recursive saturation in particular starts to play a big role. And you have Smerinsky's papers, you have direct recursion theoretic proof of Kirby, Paris, Goodstein. You have something I'm fond of, Harrington's solution of McAloon's problem. The problem, simple. Construct a model of Peano arithmetic with arithmetic operations, but non-arithmetic truth set. And he came up with a dazzling proof, meaning there was like a page and a half of handwriting and some call upon a fixed point theorem involving an oracle. Chaim Geifman and I remember we were trying to decipher it in Paris. The first person I knew who I think really understood this proof, besides Leo himself, was Dave Marker. And then, again, in connection with recursion theory.
Look, this is, it's been already 40 minutes and there have been no interruptions. So I feel like I'm obliged to interrupt just a little bit on your last remark, because I don't remember the year exactly, but it was exactly the year where Harrington proved this result. And Angus McIntyre was visiting Warsaw and was giving us lectures on the proof. So he might, and Dave was Angus's student. And I remember very well, he gave a series of several lectures on the proof. And at the end, he finished and he left his notes on a desk in this small seminar room that we had there. And somebody said, wait, you forgot your notes. But then he says, I don't need them now. I have them in my head.
But yes, Dave was a student of Angus at Yale. So, right. So I got to get Angus's name in there as the first person to really get it. Right?
Well, I'm not quite sure about the days, but he might have been.
Thank you. Yeah, but so anyway, quickly, there's been a connection. We noticed going back to already to the Paris-Harrington theorem, say that there was a connection between anti-basis theorems in recursion theory and these combinatorial independence results. And namely, you show there's a recursive something, but there's like you could have a recursive partition of n tuples, but the only homogeneous set had to be at least as complex as the nth plus first jump. You had results by Yakush, results like that anti-basis theorems, and so we sort of found a way of turning them more systematically into combinatorial independence results. Now, the field then started to spill out and connecting up with other fields. You had Wilke's proof of Gromos theorem on groups of polynomial growth using models of arithmetic. This was a very, very beautiful thing. And he first, he gave a talk on this at a meeting. It was well-attended meeting at Brooklyn College. And Kirby was there, Attila Mate, some of you must know, Wilkie himself, yours truly, I was there. Basically, it was a meeting sponsored by the computer science department, but we figured that, this work, we just sort of snuck this in, so to speak. And it was very beautiful, a very good meeting, very nice meeting. And very beautiful theorems. But then a lot of spill out, the complexity theory. We had results on finite reachable Petri nets. This was sort of fun because it used large finite sets to give an upper bound for a decision procedure that Meyer and what's his name? That some guys in computer science had crafted. Jeff Paris had some very important notes on the subject. Peter Klote worked on it. And then you had Itai's muscular paper on finite Borel sets. This again, I mean, this is really raised the ante in terms of technical wizardry. And in particular, he produced models where you had an integer in one and an integer in another. So the integers themselves were isomorphic, but they had, one was even in one model, the other was odd in the other model. And that gave a new proof of a theorem from theoretical computer science on circuits of bounded depth. So he gave a super polynomial lower bound to the size of circuits of fixed depth, computing the parity function. Now, another thing that came out of this is a lot of work on subsystems of Peano arithmetic. You had Aaron Voigt Jensen, Sijelski's work. Now, he had this paper in that volume I mentioned before from that year in Paris. And Patrick kept the faith in that he went on to be an organizer along with Dimitrakopoulos of les Journées sur les arithmétiques faibles. And then you had lots of papers, K. Paris and Dimitrakopoulos on induction schemes. And as I say, Dimitrakopoulos also is part of this Week Arithmetic Days project that's still going on. You had Sam Buss doing badass proof theory, and Laurie Kirby doing lots of things, including functional formulations. Some of Kirby's papers look at arithmetic where you don't use the standard sort of formulation in terms of plus and times and induction, and when you change the language or the formulation, it's amazing how different things look. It's very pretty. Now, finally, and I'm coming to the end now. So by the 1990s, the subject sort of had its identity now, and all sorts of things are happening. In fact, and to skip down to the third bullet here, macho model theory. I mean, all of a sudden now you have Cossack, Schmerl, Lescar, and others, doing really, again, a very solid model theory connection with this subject. You had the book by Hayek and Pudlak. You had the book by Cossack and Schmerl. You had Richard Kay's book, Kotlarski's posthumous work, the CUNY Mopaz Zoominar, and of course those Journées sur les arithmétiques faibles. So, these are now. This is a now this is a well-defined subject that which is very broad, but it's managed to need KNEAD need all of these ingredients into a solid structure. But life in today's world being so grim, I'll end with this slide. This is a slide of email I got from Patrick Sijalski, who is again working on these days of weak arithmetics. And this year, this year the group had to cancel the meeting. It's canceled the meeting that was scheduled for June in Moscow. So this crazy war in Ukraine, I mean, it it affects something so elegant and beautiful, as this, days of weak arithmetic. It was going to be. And so I wish to inform you that JAF 41 was officially canceled by the steering committee following the United Nations overwhelming resolution concerning the Russian invasion of Ukraine. Then very nicely, he says, of course, we have to recognize the hard work of our Russian colleagues to organize an issue which looked promising. So, I mean, it's a sad note to end on, but but it does show how the subject has reached out, by now to, to various corners of the world, and has its adepts, its as practitioners, and and we can wish it Godspeed. Amen.
Okay, thank you. That was great. Let's all thank. That deserves an unmuted clap from me at least. But that was very good. It was, again, I said this to you. Cornell was very nice to see the history, but it's great to see that again. The one drawback of Zoom is that you could not hear me cracking up throughout the entire presentation. It was very good. So I thoroughly enjoyed it. One of the nice things about Zoom is that many of the names that you dropped are actually here, and so it's really nice to see all of that. And we can open up to questions or comments from particularly any of those who were name dropped. Feel free to jump in.
I have a question, Ken. Not having worked in the field for a long time, what's the future?
Well, myself, I'm not the right person to ask. I really haven't worked in the field myself since, say, 1985. So that question has to be asked of Roman, Jim, Roman, say, or
Ken, I think this question should be asked of Attar, but
yes, that's a good point. Yes,
Peter, but I was actually going to say something similar. I just one small thing to add to some of the slides when Jim Schmerl's work was mentioned, and because this work in model theory of non-standard models goes on, and essentially he's the only person who's pushing it forward. And then in connection to McDowell-Specker theorem, you mentioned that paper from 2006, but those papers are coming up. And every year there is a new paper by Jim, which is essentially some new and improved version of McDowell-Specker. So I think those should be recognized and read more widely. But another thing that I wanted to say, that I remember that in the 80s, when I was at some conference where there are many talks related to arithmetic, and all this work was being done. But I talked to Jan Krajicek, Czech, model of arithmetist as well, who said, it's all very fine, but where is it all going? And he was asking me, the discipline needs a major open problem. And he says, please tell me, what is the major open problem? And the thing was that I couldn't really do it convincingly. I didn't know what was the main open problem. So maybe people who are here, maybe you would know what those problems are. I could suggest some open questions that are well known and in the small group of people who work on them. But we're lacking this like one major open problem that everyone would work on.
Well, I have one, Roman. You know what?
Great. All right. No, I know those. Okay, but say it.
Scott's problem has never been solved. The question of whether every Scott set is the standard system of some model of arithmetic. We know this equivalence for countable models, for models of omega 1 if CH holds, and we don't know anything else. For models of omega 1 in general, for models of size omega 1, but we don't know anything else. And this has been my favorite question since graduate school. And I stopped working on it because it looks quite hopeless. But I think it's a great open question that people should go back to and start working on again.
Yes, definitely. And I think this is well acknowledged that this is really a problem in set theory. But who knows? And I had a chance to talk to Todorcevic about it. And, we know that Hugh Wooden did some work on it. He tried. And I talked to Todorcevic. He did not know about the problem and got intrigued and thought about it for about, I would say 5 to 10 minutes. And then he says, oh, well, the forcing techniques we know wouldn't be enough. I don't know how he knew that, but he somehow said that.
Yeah, but I think it's something that people should maybe start. I mean, I think it needs a combination of both. I don't think only a set theorist would be able to do it. I think it needs to be someone that knows a little bit, at least of both fields. And but yeah, I mean, this is a great big question that has never been solved.
So Vika, would you like to be the Hilbert of this situation? And write down 23 problems for us?
I think my current thing is limited at that plus whatever the consequences of it.
Well, there is a list of problems in Roman and Jim's book, and I think there's this problem, and I think there's a problem from Friedman about the order types of models of uncountable models of arithmetic that are both sort of, I think, would be very attractive to to people who don't study models of arithmetic as well. And if I could interject a slight comment here, I think that all of these sort of really interesting problems kind of get at why the future is so unclear, because these are not really, as Roman said, these are kind of, some of these questions spill over into set theory or into other areas. And so there's a lot of interesting questions that are used in reverse mathematics or in non-standard analysis or things like that, with things we've been hearing about at MOPA recently. It's sort of less self-contained a field as perhaps it was in the past.
Yeah, so on that note, I just want to say, maybe you have seen it in the recent issue of JSL. There is a paper by Benedict Löwe and a co-author on Friedman's 14th problem, on the problem of order types. And it's a nice summary of what's open. Much is open, but also they managed to push something. That's a question also about fragments. So this problem is very much alive. I was happy to see that. But if I were asked now, what I think is a major open problem, and I think again is that's really essentially due to GEM, is every finite lattice representable as a lattice of elementary substructures of a non-standard model of PA. This goes back to the paper of Haim from 1976, and many special cases have been solved. Distributive lattices, the problem is known about those and many other lattices. But it's a very problem. It's very simple to state, and there is much that is known. There are various techniques, and the problem is open with connections to things in lattice theory and perhaps even in number theory.
Mm-hmm.
Well, Roman, thanks for bringing that up. I like that problem.
I think Haim has a question. Or actually a comment. Hein, were you raising your hand?
Yeah, go ahead, Hein. You're muted.
Oh, you're muted.
Okay. About 6 years ago, when this was before the COVID and in a much easier atmosphere, when I visited Israel and I spoke with Aaron Shelach, and he said that he's sure that there will be a method of forcing for Peano arithmetic, or a method of forcing for arithmetic. And I asked him, do you have any idea how it will be done? And he said, I have no idea whatsoever. And then there appeared also at the FOM from time to time this question, and my own intuition is that there is no method of forcing for Peano arithmetic. And I have also a kind of a scheme how to prove it, but I really didn't look at it more carefully. And the idea is that if you take forcing, you can do the whole thing with Boolean valued models. And on my view, Boolean valued models is a superior way of doing it, because it doesn't kind of pull you into the direction of extreme Platonism, that there is some structure of such and such a thing, because Boolean valued models really give you an independence proof simply by taking the values instead of 0, 1, but to be in some other Boolean algebra. And then you can see that there is certain statements are not provable. Now, if there have been a method of forcing for Peano arithmetic, I think it should be able to develop into Boolean valued. And then the question is Peano arithmetic sufficiently rich to give us the structure of Boolean valued models? So this is which will go there. And my intuition is that it is not that rich. Another question, but this is a more, can we have access to your shared slides? Or can we get, can you?
Sure. We can send them to everybody.
Yes, if you.
Oh, I will certainly send them to you. And if anyone else would like them, just let me know.
Okay.
Yeah.
Okay. Great. So Cameron has his hand up. So go ahead, Cameron. But before you speak, I actually would point out that Cameron did at one point attempt, along with Corey Switzer, to develop some sort of notion of forcing using using the second order structure of a model arithmetic, and
we couldn't make it work
at some point. Yeah, I think at some point,
like many hours over that.
Yeah.
I mean,
so go ahead.
Corey is much better at this than I am, and even with that, we couldn't do it. But this earlier talk about models of arithmetic overspilling into set theory kind of motivates my question. So this is maybe biased towards my interest, but there's this sister discipline to models of arithmetic, models of set theory, with interesting overlap between what transfers, what doesn't. And I was curious, Ken, whether you had anything to say about that connection, or if it's just not so germane to this historical thread.
The short answer is no, I don't know, but it's a very natural question, because yes, I mean, to begin with, you can think of Peano arithmetic as being as axiomatizing the hereditarily finite sets, right? I mean, so, and the fact is that recursions now, with generalized recursion theory, recursion theory on the integers now you can do recursion on hereditarily finite sets, which extend, and then recursion theory on admissible sets and models of set theory. So, through the recursion theory is sort of a channel of communication between the two areas. A thing that strikes me when you see, when Gödel's in, when you sort of go back to 1931 and you say, here are people taking Principia Mathematica or Zermelo, Frankel's set theory, and actually imagining or supposing that those symbols of those axioms and those could actually capture all the information that's in a structure like the integers or a structure like the universe of sets. It seems naive looking back on it, that something so flimsy as a formal as a theory with some little list of axioms compared to the sinew and structure and muscular strength of a full-fledged model of set theory. It seems funny. So a standard model of set theory. There was is second order arithmetic set theory for you?
I'd say yes. That might be
Okay.
controversial.
Well, there is a connection, of course, in Friedman's work. A lot of that impacts second order arithmetic. In particular, I think Friedman developed a version of an indicator in order to prove there was no minimal model of second order arithmetic.
Mhm.
No minimal non-standard model. I think I have that right. Maybe Laurie Kirby is here, I think, and maybe he could speak more to that.
I can't remember.
Sorry, Laurie, sorry for putting on the
But
spot.
while I'm here, I have a question. Why did Girard think that assigning epsilon 0 to PA was stupid?
He there like you, it's hard to remember exactly. I mean, and that's why he come up with this result where he assigned a different order, gamma 0, to piano arithmetic. So his point was that the question was kind of, it wasn't definitive, that look, you can assign this other zero, this other ordinal just as easily, or maybe not quite so easily, but also to piano arithmetic, that the assignment wasn't definitive. I mean, now, for example, get back to, saying that Gensen's results about epsilon 0 arithmetic struck us as, mystical or strange or something. We didn't quite understand. But if somebody had said, like the Ketten and Solovey paper, I said that, epsilon 0 is the ordinal up to which you have to go in the hierarchy, in the Wiener hierarchy, in order to capture all the provably recursive functions of piano arithmetic, right? All the recursive functions are provably total in piano arithmetic. That would have made much more sense to us.
Okay, Roman, why don't you go ahead?
Well, I just want to just add one more comment, because when we were at Cornell, there was this short discussion about the number theoretic content of independence in piano arithmetic. And I said that I remember something that Mostowski wrote at a certain point about this possibility of using non-standard models to obtain arithmetic independence result or number theoretic independence result. And my memory was kind of vague. And then Laurie asked, about what was it that Mostowski actually said? And I found this quotation, and it's not really that stark that I thought it was, but I just want to read it to you quickly because I just have it here. Okay, so this is from his from this booklet that he wrote, 30 years of foundational studies. He wrote it in 1966, and it's already after Cohen and Forcing. And he says something like that we should mention here results obtained among others by Pfefferman, Scott, these authors jointly with Tenenbaum and Rabin, which show that there are no recursive non-standard models satisfying the Peano axioms. All these results explain why it is so difficult to establish the independence of number theoretical sentences from the arithmetical axioms by the use of non-standard models. In order to find such applications, one should have a much better knowledge of the structure of these models and more direct methods of their constructions than we have at present. Okay, that's what Mostowski said in 67. I remember when I was reading this as a student, and it was in the 70s, and I already knew about the work of Kirby and Paris. And I thought then that Mostowski was somewhat prescient that somehow, this method of indicators and analysis of initial segments of models of PA, this was exactly the thing that was needed, from the better knowledge of the structure of non-standard models. But what Mostowski says here is something quite general. But I still like the quotation.
Thank you. Are there any other questions or comments?
Yeah, I just wanted to say, of course, I've been working in things like provability logic, and so it's not really model theory, but there's one great open problem there, and that's the provability logic of S12 and I delta 0 plus omega 1. So, but everybody got so scared of the problem that nobody dared to try it in the last 10 years. So it has been open, but completely dormant.
I believe this is what Ken referred to as, quote, badass proof theory. on one of his
it's not clear what it is, so nobody knows what the relevant methods will be.
But on that note, so perhaps I should also mention that something that everyone knew when in the 80s, there was all this list of problems about provability in I delta 0. And
yes.
And so I still think that and it shouldn't be forgotten. But when I talked to Leszek Kołodziejczyk about it some time ago, he said that those problems turned out to be so hard that no one really wants to touch them anymore. And one of them, which I think for us is fundamental, is whether delta 0 definable sets form a hierarchy with respect to the number of quantifiers.
Right.
So right. And it's really a scandal that we don't know that. But it doesn't seem that anyone is working on them. Do you know, Albert?
No. I don't know, but I think nobody is working on it. But yes. So what I can, there is good news, but of course nobody here is so much interested in the constructive case. But there is now the claim. There is a claim by Mujtaba Motahidi that he solved the problem of the provability logic of Heiting arithmetic. So that was the second great open problem of provability logic. And so there is now a hopeful claim. So I tend to believe that he solved it, but it still has to be checked. So in the constructive case, there is some real progress, but in the weak arithmetic case, the whole thing is still completely open. And as so this problem, I think, is in the niche of the problems that Roman mentioned, so that everybody is scared of it.
Okay, all right, so I think this will be a good time to wrap up, and let's all thank Ken again. A very excellent talk, again, as it was in Cornell, so I'm glad we got a good audience for this.
Thank you.
And I'll stop the recording.